Okay, so to describe or show what's going on with this battery and this copper wire, and to explain the physics behind what's going on, we've drawn a couple of free body diagrams and we've come up with a simple derivation to prove Lorenz's law to be accurate. This first free body diagram shows a battery in a vertical placement. The current, I, is moving from bottom to the top and transferring into the copper wire. And then we also have this length L, that's the length of the battery. The magnetic field on this side is actually moving into the wall, and on this side it's coming out of the wall, so it's rotating around the current. The force vector is 90 degrees from the current and also perpendicular to the magnetic field as well. To show this a little bit better, I've got a two-dimensional drawing here. This shows the top of the battery. We're looking down onto the top of the battery, and you can see the current. This circle with the dot in the middle indicates that the current's coming out of the battery. This B here, this vector is moving around the current. This indicates the direction of the magnetic field, and this force vector is always perpendicular to the magnetic field as well. This is part of what's called the right-hand rule. So if you have a current, back to this one, moving up, you wrap your fingers around the current, and that's how the magnetic field moves. And then of course the force is always going to be perpendicular to that magnetic field direction. Over here we've got our derivation. We start out with Newton's equation of motion, force equals mass times acceleration. Acceleration can also be written as the time derivative of velocity. Or you can rewrite this whole equation as mv over delta t, and you can see mv is momentum over a time interval, so we've got some sort of momentum over a time interval. And this can also be written as m over delta t times v, and this m over delta t is the key here. This is indicative of what's called a mass flow rate, and the relationship between mass flow rate and the magnetic field and what's taking place is the Q and the B and sine theta. Q being the amount of charge that is moving through the magnetic field. This is also known as magnetic flux. Sine theta indicates the angle at which the charge, or the amount of charge, is moving through the magnetic field. And we still keep velocity. Then we rewrite velocity as length over time, L here, and delta t over here. This Q over delta t is the amount of charge that's moving through a cross-reference area over a time interval. This is also known as current. So once we rewrite everything here and replace Q over delta t with I, we ended up with I of LB sine theta. And since theta is always 90 degrees, we're just left with current times length times magnetic field. And that's Lorenz's law.
By placing the wire over the magnets, which creates an upward current that moves through the battery, the current then induces its own magnetic field. By using the right-hand rule, the magnetic field wraps around the current, thus creating angular momentum. As you can see, it moves in a counterclockwise position following the right-hand rule.
Here in the second experiment, we can see that the magnets are on the other side of the battery, causing the current to go downwards. The wire now goes clockwise around the battery due to the Lorentz force, which can be visualized with the right-hand rule once again.
An application of Lorentz law that can be seen today is in the new Tesla models. They take electrical power and convert it into mechanical power. The electrical power comes from a series of magnets that create a magnetic field, thus following Lorentz law. This could lead to people becoming less dependent on non-eco-friendly fossil fuels and going towards a cost-effective and fuel-efficient vehicle like Tesla.